Howdy, and welcome to Mean 410 and Mean 611 internal combustion engines and advanced internal combustion engines, supplementary lecture video for compression ignition combustion. So about a week or so after the end of the spring semester, I got an email from one of your colleagues in the class, and he was interested in having this lecture because if you remember, about midway through the semester, of course, I know you'll remember this, we had to cancel classes for the university right the week after spring break due to COVID. And what that meant for internal combustion engines was basically the removal of the last week of class, which is when we would have covered compression, ignition, combustion. And so the thought was, well, in spite of the fact that we didn't necessarily formally have it part of the class and wasn't part of any of your formal assessment criteria for the end of the semester, we can still generate this video and teach you at least some of the high-level basics about compression, ignition, combustion. So I agreed, and now about 3 weeks later, I'm finally able to get to it. So I apologize I didn't do this in a more timely fashion, but nonetheless, here it is, and hopefully you still have interest in internal combustion engines and in learning at least some of the basics about compression, ignition, combustion. Now, I do have to say that one of the reasons why I was a little delayed on making the video is because the new video recording technology that I had ordered, basically an iPad Pro, had finally come, and apparently it had arrived mid-April, but someone at the university didn't tell me, and I didn't know, and so I didn't get the new technology until about mid-May, and it's literally taking me this much time to figure out the best way to generate these videos to be able to provide them for you. But what's really cool is that I can write on the screen, and it's like super nice. So I'm super excited. I really wished I had this throughout the whole semester because literally I'm like, laying on the screen as I write this, right? So it's a lot of fun. Anyway, this isn't about iPad Pros. It's about compression, ignition, combustion. So let's go ahead and get started on this supplementary video lecture in spring 2020 plus semester. Okay, so basically the objective of this chapter is to capture the essential features of compression, ignition, combustion, right? So by the time we're done with this, you should be able to characterize the general features of engines that employ compression, ignition, combustion. And of course, by and large, those engines are what we commonly call diesel engines. And also to identify the primary processes of compression, ignition, combustion. Okay. Now, before we get too far, what I would like to recommend to you is that you check out this really cool YouTube video. You should just be able to click on that link there, or copy and paste it into your browser. And essentially, it's a 1952 video that was produced by Shell that describes the history of diesel engines, even back before Rudolf Diesel had even conceived his concept, taking you back to even some of the older engine technologies that were sort of precursors to Rudolf Diesel's, innovation or invention. So definitely watch it. It's only like 18 minutes long, and it gives a really nice history of some of the precursor technology. And I learned quite a bit by watching it. And what's fascinating is that if you think about it, even from a entrepreneurial or an innovative spirit type of a mindset, it's really neat to see the groundwork, the framework that Rudolf Diesel was building his technology upon, right? A lot of times I think when we learn about inventions or discoveries or things of that nature, we sort of assume that the person who came up with it just invented this out of their mind. And maybe that happens every once in a while, but by and large, most people are building upon, what seems like incremental work of others before them, right? And so check it out. It's really cool and gives you a good background about that engine technology. Okay, so what are the characteristics of compression, ignition, combustion? Well, first of all, And these are just major characteristics, right? In other words, when we look at engines that employ compression, ignition, combustion, we usually find these main features, right? And you could, if you wanted to, contrast this to other engine technology like spark ignition combustion, and I'll even maybe do that a little bit as I go through this, just to compare and contrast what we talked about at the end of the semester in the context of spark ignition combustion. So first of all, compression ignition combustion engines, right? They're relying on high compression ratios to basically ignite the mixture, right? So they generally have high compression ratios. That would contrast, say, for example, to spark ignition engines, where, as we talked at the end of the semester, really the last thing we talked about last semester was the fact that spark ignition engines are actually limited on their compression ratio because you start to run into something called fuel knock. Well, compression ignition engines, they're relying on that compression for ignition. And so you want that compression ratio to be as high as possible. Usually speaking, compression ratios for CI engines usually operate somewhere between 12 to 18. Every once in a while, you might get up to 19, right? Even 20. But the moment that you start going into a compression ratio of 21, what actually ends up happening is, let me just stop for a minute and real quickly remind you, right? We all know what happens with efficiency as we increase compression ratio, right? The higher the compression ratio, the higher the efficiency. Remember this curve that we generated early on in the semester, right? Where we said, okay, that's what our efficiency curve looks like. Well, this, of course, as you might recall, this is an ideal efficiency, right? If we were to go ahead and plot what happens with a real engine, the efficiency curve actually looks like that as we increase compression ratio. And this peak is somewhere, it depends on engine design, but it's somewhere around that 21 mark. And what's happening as we go to higher and higher compression ratios is your friction actually starts to create so much loss within your bearings and your rings and your other, metal to metal contact points. The higher the pressures, the higher those forces, therefore the higher the friction losses. And so your actual efficiency will actually start to decrease as you raise compression ratio higher and higher. Your in-cylinder thermodynamic efficiency may continue to increase, but your brake efficiency is going to eventually start to decrease, right? So generally speaking, engines are practically operating in the range of 12 to 18 for high compression ratios, right? Okay, so in this, is kind of our first indication of what's going on with with a compression ignition combustion engine, and that is that the fuel-air ratio mixture is in fact being ignited by the relatively high temperature that is created by the high pressure of the high compression ratio, right? And so, of course, we know that pressure actually inhibits ignition, but high temperature promotes ignition, okay? And so we're using the fact that it's a high temperature environment to be able to support that ignition process. But I want you to keep this idea in mind as we talk about compression ignition combustion, particularly in the context of ignition characteristics of engines, right? Of fuels, excuse me. Remember how we talked about the influence of pressure on things such as ignition and laminar flame speed and things of that nature, right? So keep that in mind as we talk about the types of fuels that we choose, that we use to help promote the combustion process. Okay, so we also know, right, that load control through fuel metering, or that load is controlled through fuel metering as opposed to a throttle, right? Remember that a throttle is restricting air, right? The engine is like the human body. It's just trying to breathe air, okay? And so in conventional spark ignition engines, for example, which usually use a throttle to control the load, and they do that by literally restricting the amount of air that the engine can breathe, and so that's necessarily going to inhibit the power that the engine can make. And ultimately what that throttle is doing is it's reducing pumping, it's increasing pumping losses, right? The throttle is increasing pumping losses. When you remove the throttle, it reduces the pumping losses. And so you get, say, an efficiency benefit by having your load control be done through fuel metering. Okay, now again, reflecting on what we talked about during spark ignition combustion, we spent quite a bit of time talking about the idea of maximum brake torque. And if you remember, we discussed maximum brake torque in the context of there being a spark advance that limits the maximum torque that an engine can make, right? Well, what is that concept in the case of a compression ignition combustion? Because we don't have a spark timing, we don't have a spark advance in a compression ignition engine like we do in a spark ignition engine, right? So in the case of a compression ignition engine, the maximum torque is actually limited by something which we call the smoke limit, okay? Now, what happens is and we'll go over this more in the next few slides, but just if you could spend a moment visualizing with me what actually happens during compression ignition combustion, right? So you induct pure air into your cylinder, and this pure air gets compressed during the compression process. Remember, there's no fuel in the cylinder, there's no fuel in the mixture yet. And the piston approaches top dead center. At that point, fuel is injected into the cylinder, and that fuel then has to go through a long series of physical and chemical processes before ignition actually takes place, right? So you inject that fuel into the cylinder, and you have to do a whole bunch of stuff, right? First of all, the fuel has to penetrate into the mixture, right? So remember, the air has been compressed, right? It's at a pressure of, say, 50 bar, right? Could be somewhere between 20 and 50 bar, so 20 to 50 atmospheres. Go 14 psi times 50. That's the pressure in psi in the cylinder when the fuel is being injected. And so you have to, first of all, inject the fuel at a pressure that is higher than the compressed air pressure. That's number one. But if you only had it marginally higher pressure, right? So say your air pressure is at 50 psi and you're injecting the fuel at 65 psi, well, that's only a 15 psi, that's only a 1 atmosphere pressure difference, right? So your garden hose, for example, has a larger pressure difference when you open the water spigot, the faucet, to spray water out of the garden hose, right? And you see how relatively low momentum that has. Now imagine that being fuel injected into the compressed air environment of an engine, right? You need a lot more penetration, a lot more momentum, a lot more fluid power, fluid energy to get that fuel injected into the cylinder. So you end up increasing the fuel pressure substantially, right? Sometimes at least an order of magnitude, in some cases even 2 orders of magnitude higher than the pressure of the compressed air that it's being injected into, right? And so that then allows you to do what we call penetrate, right? The fuel penetrates the cylinder. It cuts into that compressed air environment. And so you basically have this liquid stream flowing into the compressed air, okay? So now, again, visualize with me. So you have this liquid stream of fuel penetrating into your compressed air environment. And as that flow penetrates, it starts to mushroom, right, toward the leading edge of the injected fuel, right? So the fuel that's furthest away from the fuel injector starts to mushroom out, right, and kind of get entrained by the air, okay? That mushrooming out is what we call spray breakup, okay? So you have penetration, you have breakup, and then once you have breakup, then you have another layer of basically fluid particle breakup, if you will, or another scale of fluid particle breakup, which we call atomization, right? So you take that spray that's breaking up and you break it up even more, right? So that you have a larger volume of liquid fuel composed of smaller and smaller liquid fuel droplets or particles, okay? So penetration, breakup, atomization, and then finally the last one is vaporization, okay? So you have to do those 4 physical processes: penetration, breakup, atomization, and vaporization in order to get the fuel to the point where it can chemically ignite, okay? Those are all physical processes. One thing to always remember, physical processes always take longer than chemical processes, okay? So those physical processes can literally take milliseconds, whereas the chemical processes can take microseconds, right? They're at a much smaller, shorter time scale, okay? Okay, so how does this all relate to smoke limitation? Okay, well, now, imagine that you're, running the engine and you're trying to produce torque. So you're injecting a certain amount of fuel into the cylinder. And let's just suppose for a moment that that fuel that you're injecting into the cylinder creates an equivalence ratio of, say, 0.6 in the cylinder, right? Overall lean, okay? Fuel air equivalence ratio of 0.6. Now, that gives you a certain amount of torque. You want to make more torque. So if you want to make more torque, what do? You increase the amount of fuel you inject. Well, now you increase the amount of fuel you inject to 0.7, okay? And then you increase it to, say, 0.8. And what happens? Well, as you inject more and more fuel, now you're adding more and more time to the physical processes that have to take place before that fuel can ignite, okay? And you create what is called locally rich regions, which basically occur when the, certain parts of that injected fuel, right, the fuel that's injected say the first droplets of fuel that are injected, they undergo those physical processes and chemical processes rather quickly. And so they ignite soon as you're injecting more and more fuel into the cylinder. So the first fuel that's injected ignites, it raises the temperature of the mixture as you're injecting more and more fuel into the cylinder, okay? And eventually what happens is that your in-cylinder mixture temperature gets so high that the last droplets of fuel that you inject into the cylinder don't have enough time to undergo all the physical processes that they need to burn cleanly. And instead what happens is you end up starting to basically pyrolyze your fuel, okay? In other words, you create little char particles or, what we scientifically call soot particles, okay? So soot is basically what we would call a pyrolyzed hydrocarbon or a fragmented hydrocarbon, right? In other words, that hydrocarbon underwent a chemical reaction, not necessarily a oxidation reaction, okay? And so you take this, this C18 long hydrocarbon chain and you subject it to a high temperature where it basically fragments into some radicalized complex form of a hydrocarbon that basically stabilizes itself as a soot particle, okay? And so when you analyze soot, for those of you that are really interested in the chemistry, when you analyze soot, soot is basically a collection of what we call polyaromatic hydrocarbons, okay? And the polyaromatic hydrocarbons are formed through the fragmentation of ordinary hydrocarbons that are in your fuel that they basically aren't allowed to undergo all those physical processes before the full ignition process takes place, okay? So you generate soot, and now soot is basically this, it's kind of sticky, right? You've probably touched soot before in your life, or you've interacted with soot in like a fireplace or even a grill, right? A cooking grill, barbecue grill. And so, it's kind of sticky and stuff can easily bond to it. And so your soot then starts to act as an attractor for other particles within your mixture. And that could be other liquid hydrocarbons. It could be gaseous hydrocarbons that can bond to the surface of the soot particle. It could be non-carbonaceous, non-organic substances like any sulfates that might be in the mixture as a result of there being sulfur in the fuel. All kinds of stuff, right? You take all of that, you put it together, and you have what is called particulate matter, okay? Particulate matter is basically any particle matter that you can collect on a filter, okay? So when you're running your engine, and if the engine is producing smoke or soot or particulate matter, to be more scientific, if you pass your exhaust through a filter, okay, everything that you collect on that filter is going to be considered particulate matter. And the bulk of your particulate matter is soot, and that's basically what smoke is, okay? So as you go to higher and higher fueling levels at any given load condition, you're raising your in-cylinder equivalence ratio but you're making it more and more difficult for that fuel to undergo all of its physical processes before ignition, and you end up generating high and high concentrations of smoke or soot. And you can actually generate so much smoke that it actually begins to deteriorate your combustion efficiency, and your engine torque can start to go down, right? So a lot of times people will ask me, why don't diesel engines operate at stoichiometric conditions? And the answer is, well, because they can't produce enough torque, right? I can produce more torque at a lower equivalence ratio, right, than if I were to try and run that engine at stoichiometric conditions. Yes, it is also true that if I'm running the engine at stoichiometric conditions, my engine would be smoking like a bushfire, right? It would basically look like, a turn of the 20th century smoke pipe, right? Just black smoke pouring out. But that's not why engineers back in that day, regrettably, would not run an engine at that condition. Believe me, if the engine made more torque, producing that much smoke, they would have done it, because that was their mindset then, right? They were trying to produce torque. They were trying to produce power. But they were making less torque. And so they scaled it back, the amount of fueling, so that they could achieve the peak torque, okay? And so in the case of compression ignition engines, you generate your maximum torque at the condition where you start to run into the smoke limit, okay? So as a result of that, diesel engines, of course, typically operate lean, right? You know about this. We've talked about this all throughout the semester, right? And so now when you take a look at this, you say, okay, well, compression ignition engines operate with higher compression ratios. That has a tendency to raise efficiency so long as you're within a reasonable range of compression ratio. I take this nasty entropy generator, the throttle, and I send it to the museum, control my load through fuel metering. So that has a tendency to raise efficiency. And I operate the engine lean. And as we learned this semester, the semester plus, when I operate the engine lean, that has a tendency to raise my efficiency. So 1, 2, 3 fundamental inherent features of compression ignition engines raise efficiency, right? And that's why, quote unquote, diesel engines are considered more efficient than their spark ignition counterpoints. It's nothing to do with the fuel. I've heard people say that, right? They'll say, well, diesel engines are more efficient because the diesel fuel has a higher heating value. Absolutely not true. First of all, as you've already seen, diesel fuel and gasoline have almost identical heating values, which makes sense because they're both composed of long-chain hydrocarbons, right? So that's where your heating value is basically coming from, is the nature of the hydrocarbon. But secondly, you also learned this semester that efficiency doesn't depend on the amount of energy you give something, right? The more energy you give it, the more work you expect out of it. So there's something more inherent to the design of a diesel engine than just the type of fuel it uses. And it's these reasons, okay? Now, of course, it is true that the fact that we're using compression ignition combustion gives us these features, right? The use of compression ignition and compression ignition gives us the need for a high compression ratio, right? It enables us to deobligate from using a throttle to regulate a homogeneous fuel-air mixture, right? We can use a heterogeneous fuel mixture and control load through fuel metering because of compression ignition, right? Our engines are operating lean because it's a heterogeneous mixture, because it's a compression ignition combustion, okay? So all of these things all feed into resulting in a higher efficiency. And as you'll learn when you watch that video, that YouTube video, that is exactly what Diesel was after. He was absolutely after the higher efficiency. He didn't necessarily know all of these things, right? He was actually looking to what his main motivation, believe it or not, was he saw that the new auto engine was very efficient, and he saw that it was an internal combustion engine, and he was really actually going after the steam engine. He was trying to come up with a more efficient way to generate power in place of the steam cycle, right? And he saw the efficiencies of steam cycles. You'll see in the video that those were like down in the cellar at like 4%, okay? But the new auto engines and the other spark ignition engine variations were all in the range of, 10 to 15%. And he's thinking, my goodness, I can more than double my efficiency by going to an internal combustion engine. But the challenge that he had was that the steam engine was using things like heavy oil and coal, right? So he had to figure out how to ignite that heavy oil and coal, and hence he fell on compression ignition, okay? It's not like Diesel sat down and said, well, I'm going to maximize this, I'm going to maximize this, I'm going to maximize this, and boom, there's my engine, right? Again, he kind of stumbled upon it. And that's, again, from the entrepreneurial innovation type aspects of things, I find that rather fascinating. Okay, so, this last little bit here, right, present day technical limitations of fuel-based load control, basically result in a heterogeneous combustion mixture. And what does that mean? It means that there's both spatial and temporal variations in the fuel-air mixture ratios, and there can also be spatial and temporal variations in the phase, right? In other words, you have liquid fuel, vapor fuel, and as we just got done talking about with particulate matter, solid particulate, all existing in the cylinder at the same time during compression ignition combustion. Okay, so what are the processes of compression ignition combustion? There's going to be a little bit of overlap here with what we've already talked about with spark ignition combustion, but this will certainly look familiar, this curve here, right? This is the volume versus the crank angle, the engine crank angle, right? So TC here, of course, is top dead center, right? And BC is bottom center. IVC, intake valve closure, EVO, exhaust valve opening. You remember all these good details. But of course, the piston starts at its bottommost position, right? Maximum volume, moves upwards, so the volume decreases until it reaches a minimum volume at top dead center. And because of the kinematics, reverses its direction, right, and starts to expand the volume. And then eventually the piston reaches bottom dead center again, okay? Okay, now where there is departure, so of course this is, just to create a frame of reference, this is the compression process, right? This is top dead center, and then this is the expansion process. So combustion, right, is going to start somewhere around here when the piston is at top dead center. So of course, if this were a spark ignition engine, what you would do is you would, be drawing in during your intake process a mixture of fuel plus air and compressing that mixture of fuel plus air, releasing your spark, somewhere, say, around here, and then having combustion and expansion. Well, in a compression ignition engine, what happens is you intake air only, right? So your only air is flowing past your intake valves or your intake ports, whatever it might be, and you're compressing air only, okay? And then somewhere near top dead center, and in this case, it happens to be right here. So that's what the second plot is showing us is the fuel delivery rate. I'll talk about this here in just a minute. But somewhere near top dead center is when you start to inject fuel. Okay, so this is what we're going to call SOI, which stands for start of injection, and meaning start of fuel injection. Okay. And then that injection, that fuel injection process, so this is when you are injecting fuel at a very high pressure, right? At least an order of magnitude, and mostly nowadays 2 orders of magnitude higher pressure than the air pressure inside the cylinder. So you're injecting this fuel directly into the cylinder during a period of time. And when that injection is over, you then have what is called EOI, which of course is end of injection. Okay? Now, there's a lot that happens after start of injection. We're going to talk about that actually on the next slide, so I'm not going to spend too much time about it. But basically, in short, there's a short, what we call ignition delay period. And the ignition delay period is just that time from when you inject the fuel, you start injecting the fuel, and you start combusting the fuel. Okay, so if we look now here on the third plot, the cylinder pressure is a function of crank angle, this one here, okay? Then, of course, you'll see that we have SOI, start of injection, listed on the slide. And then some number of crank angles after start of injection, you have what is called SOC, okay? And, of course, SOC is start of combustion. Okay. Okay, so now you'll notice that start of combustion. So now I can draw this. So this is all on the same crank angle, right? So this is your crank angle scale down here, right? So all four of these plots are all at the same crank angle, okay? So if I draw my end of injection down, what you'll notice is that my fuel mixture is actually burning before I end injection. Okay, so I'm injecting fuel into the mixture while combustion is taking place. Okay, so if you've ever, and again, this is where I'll ask you to visualize things with me. If you can imagine, say, a blast furnace or an oil burner, or or even just imagine like a flamethrower, right? You've got this tank of fuel on the ground next to you, and you've got this handle in your hands that basically can just blow flame all over the place. That's really a lot like what diesel combustion is like, right? When you are injecting that fuel into the cylinder, those streams of fuel act as flamethrowers, right? They're basically just issuing fuel and flame into the compressed air. Okay, so and that's going to have implications with the way the combustion process takes place. And again, we'll talk more about that in just a minute. But this ignition delay period, that's the time between start of injection and start of combustion, right? So that delta there, that is what we call the ignition delay, okay? Okay, so you have this ignition delay period, and then combustion eventually begins. And of course, as combustion proceeds, well, now your cylinder pressure starts to rise, right? So if I follow along here on this pressure curve, we've got the motoring curve, right? We're just compressing air, motoring. And if I didn't inject fuel, then my motoring curve would continue in this dashed line fashion, right? So I'd compress, reach top dead center, reverse piston direction, and then expand and expand the volume. But I am injecting fuel, right? So now my cylinder pressure rises, and then combustion begins. So now my cylinder pressure rises due to combustion, right? Reaches its peak, right? And then begins to expand as combustion starts to die down, and the piston is now rapidly expanding that volume. Eventually, I come to EOC, or end of combustion. My piston continues to expand that mixture, and then eventually I get to EVO, exhaust valve opening, and everything is done. Okay, so that's the processes of compression, ignition, combustion. And just to now sort of segue us into the next set of slides, we would say, or we would have our fuel injection profile is what this curve is profiling here. Okay, so this m dot f sub I, that's the mass of fuel injected. Okay, and so you can see that when you have start of injection, your mass of fuel that's injected rises, and then it kind of continues to rise until eventually you say, okay, it's time to end injection. So then you start to close the fuel needle valve, right? So as that needle valve closes, the mass of fuel that's introduced into the cylinder decreases and eventually gets to zero. Okay. And then the last item to point out on this slide is this bottom plot. And this is the m dot sub FB, which is the fuel burning rate, okay, the mass fuel burning rate. So it's very similar to the mass fraction burned that we spent quite a bit of time talking about in spark ignition combustion. But in this case, this is explicitly the mass burning rate. Okay, so m dot FB is the mass burning rate. Now, when you look at this, you'll notice that it has an interesting characteristic to it. You have a very sharp rise in the fuel particles that are burning, and then it actually drops. So it kind of does this spiky peak here. It drops, but then it rises a little bit again in a sort of smooth kind of parabolic fashion, and then eventually begins to die off. Okay. All right. This is a very common burn rate curve, right? So this is what we would call a burn rate curve. This is a very common burn rate curve for compression, ignition, combustion. And what we're actually looking at is we're actually looking at two modes of fuel burning, okay? The first mode is what we call premixed combustion, and that's basically this portion of the burn rate right here. And so this would be premixed combustion or premixed burning. And then the second mode is this second portion here that's under the sort of parabolic part. So the premixed burning is that spiky peak. We actually will oftentimes refer to that as the premixed burn spike. And this more sort of smooth parabolic type burning is what we call diffusion burning or mixing controlled burning. Okay. So you can already kind of tell by the names of these two types of burning that the premix burning is that burning which takes place when the fuel and air is premixed, okay? And then the diffusion burning, or the mixing controlled burning, is that burning that takes place at such a rate as the fuel can mix to a proper ratio with the air, okay? In other words, premix burning is limited by the chemical rate, the chemical reaction rate. Diffusion or mixing controlled burning is limited by the physical mixing rate, okay? That physical process, those physical processes that we described early on, that's what limits your diffusion burning rate and the premix burning. Those physical processes all took place prior to ignition, and so that rate of burning is really just limited by the rate at which the chemistry can take place, okay? Okay, so this slide here, I'll just go through this very quickly because I've already largely described this, but this in more detail describes these various processes that we talk about with compression, ignition, combustion. So as we've already mentioned, right, first of all, fuel is injected into the cylinder near the end of compression. Modernly we do that injection directly into the cylinder. There's some engine designs out there. I used to say old style designs that would do what we call indirect injection. And this is often sometimes referred to as a pre-chamber. And this is a means to be able to ignite fuels that are basically difficult to ignite in very lean environments, right? But we're actually starting to return to pre-chambers for other reasons, right? Basically emissions control. And so this is the direct injection technology is not as domineering as it was, say, in the last 2 decades. We're starting to see some reemergence of indirect injection, and again, that's what we refer to as pre-chamber combustion systems. Okay, so as that fuel injects into the high temperature, high pressure environment, it begins to mix with the air and vaporize, right? So mix with the air, right? So the mixing, that's where we have these 4 processes of penetration, breakup, and atomization. And then, of course, the 4th process I have listed in the text, and that is vaporization. Okay? So you have to do these 4 processes before the chemistry can start. Okay? You can't ignite, you can't oxidize a liquid. Okay? It has to be vaporized. And in order to most effectively vaporize your fuel, you have to atomize it to as small of liquid droplets as you possibly can, right? You really want to increase that surface area, right? Remember the Biot number? It's a little bit like that, right? Where you want to maximize your surface area and minimize your volume so that you can vaporize your droplets as quickly as possible. Okay, so as that fuel injection continues, those first portions, right? So remember that there's a time here, right? And so the first few portions of fuel that get injected, they will inject before combustion begins, right? So say, this portion of fuel injects before ignition. So as that fuel is injecting, it's undergoing these four processes of penetration, breakup, atomization, and vaporization before the combustion reaction actually starts. And so you will have a quantity of fuel that has done these four things at the moment that they're at a high enough temperature to actually begin to chemically react. And so then once that ignition process takes place, well, remember, the chemical reaction timescales are much shorter than the physical timescales. So if your fuel has undergone these four processes, right, all of that fuel that has undergone those four processes is basically going to ignite and burn just like that. It's going to ignite and burn far faster than the time it took to undergo these four processes, okay? And that's what leads to the premixed spike. That would be the portion that is the premixed burning, right? And that premixed spike consequently raises your mixture temperature and pressure, which, by the way, accelerates the atomization and the vaporization, okay? But sometimes you can be injecting so much fuel that even the higher temperature in the mixture that is increasing the rate of atomization and increasing the rate of vaporization, it still might have a difficult time keeping up with that fuel that's injecting into the cylinder, right? But anyway, that time between the start of injection and start of combustion, that's what we call the ignition delay, right? We've already talked about this. And it is governed by the rate of mixing, the rate of vaporization, and the chemical delay of the fuel, right? In other words, the ignition delay depends on how quickly the fuel can mix, how quickly the fuel can vaporize, and how quickly the fuel can undergo the chemical ignition process, okay? All right, now, once you have combustion beginning, then the parcels of fuel that continue to be injected have to still undergo these four processes, right? Mix, I put it out of order, so mix should go first. Mix, vaporize, and ignite. They can do this more readily than earlier portions because of the elevated temperatures. But eventually what happens is that a flame, right, these physical processes basically dominate the time it takes to get the fuel ready for ignition. And so then what ends up happening is you have a flame jet that develops around the injecting fuel spray that burns diffusively, right? That is, the rate of burning is governed by the diffusion of air into the fuel spray, or what we call mixing controlled, right? The rate at which the air can mix into the fuel spray, okay? And that then is what leads to the diffusion portion of the burn profile. Okay, once fuel injection terminates, right, then there's a third type of burning, which we call particle droplet burning. That'll continue, and that does so diffusively until most of the fuel is burned and oxidized. But of course, you will have local combustion mixture ratios and temperatures that will pyrolyze the fuel, just as we've talked about already earlier. That leads to the formation of soot, right? And then that will sometimes burn through, or it will burn, right, through the oxidation, through the flame sheet. But of course, you won't be able to oxidize all of that soot, and you'll have some emission of soot or particulate matter from the engine, as we had described earlier in today's lecture. Okay, so this is a close-up of that diesel burn rate that we showed 2 slides ago. And now you can much more definitively see this premixed combustion phase, right? This is consisting of all the fuel that had undergone the physical and chemical processes prior to the ignition period, right? Prior to the ignition point. And then the corresponding mixing controlled burning, right, is that additional fuel that gets injected into the cylinder during the after start of combustion, right? And then that fuel, of course, burns diffusively or in a mixing controlled fashion, and generally has a much longer burn profile to it than the somewhat dramatic and spiky premix that occurs with the premixed combustion burn phase, okay? So, of course, as we mentioned, that ignition delay is that waiting period between start of injection and start of combustion. It's during this period that the early packets of injected fuel will mix and vaporize with the air, Eventually, they undergo a chemical delay period, and that chemical delay period will commence once the mixture reaches an ignitable mixture. Now, we haven't talked about this a whole lot, and there's a lot of details, of course, that I can't cover just based on the time that we have to do this. But a fuel-air mixture will actually start to ignite at fairly rich equivalence ratios, right? So right at around an equivalence ratio of say, 2.5 and lower, you'll actually begin the chemistry, the chemical ignition process, right? And so if you've got the temperature and the lean enough equivalence ratio, then you'll begin to have your chemical ignition process. Of course, it's also these very rich fuel air equivalence ratios that lead to soot. And so a lot of the development work that's done in diesel engines is actually trying to prevent ignition until you get much leaner equivalence ratios to help avoid soot formation. Okay, that premixed combustion then, of course, rapidly burns the fuel that mixed and vaporized during the ignition delay period. Once that fuel is consumed, then you move into mixing controlled or diffusion combustion. And of course, that burns the fuel as it injects into the cylinder as a spray jet, where you have your physical and chemical processes basically taking place within that spray jet. The rate of the burning during this phase is controlled by the diffusion of air into the injecting fuel spray. And then that late combustion period, and that might only be, say, 10 or 15% of the total fuel that's burned, is diffusively burned as a particle droplet formation. And again, tries to burn as much of the remaining soot particles as possible, but not all of it gets burned, and you end up emitting some soot. Okay, so this slide, I'm not going to go through this because this slide just goes into a lot more detail about what we've already talked about. But we can spend a little bit of time talking about what ignition delay is and the sort of the two components of what we are calling ignition delay for a compression ignition engine. Now, we always have to be really uberliciously careful about this word ignition delay because it tends to get tossed around somewhat flippantly by the engine community. Combustion scientists have a very precise definition for ignition delay, and that's what we would consider to be the scientific gold standard of ignition delay. But we use it in the engine community to sort of phenomenologically represent, again, that time between when fuel gets injected and when combustion actually begins. And so consequently, when we talk about ignition delay in the engine world, we sort of lump everything into it. It's almost like a grotesquely averaged parameter that includes a lot of different processes, right? Both physical and chemical. And so, again, we've described a lot of this already, so I won't go through this in great detail. But the first portion of the engine ignition delay is what we call the physical mechanism, right? And again, that involves this penetration, breakup, atomization, and vaporization. And, the various factors that affect atomization are things like the fuel injection pressure, right? The diameter of the injector holes, the fuel fluid properties, right, like fuel viscosity and surface tension. Things that affect, of course, the vaporization are the extent of the atomization, right, the size of the droplets, the distribution, the velocity of the fuel particles, pressure and temperature, of course, inside the cylinder, and fuel properties, right, such as fuel volatility, the boiling point of the fuel. And then things that control the mixing between the fuel and the air, would be things like the injector design, right? How many holes are drilled into the injector, what the spray pattern is. It's if this is the cylinder, right? I don't have just one big, thick liquid stream flowing into the cylinder. Instead, I might have 5 or 6 tiny streams with much higher velocities, right, to be able to generate the type of momentum that we need to be able to, of course, momentum's conserved. I have to be careful as I say that. But the smaller liquid streams make it easier for the fuel to break up, right, as it reaches the leading edge of that fuel spray, reaches the furthest extents of the cylinder, begins to break up, right, and then atomize, and then eventually vaporize, right? So those little squiggle lines are meant to represent the vaporization. Combustion chamber design also plays a role in how well the fuel mixes with the air. So this is where the bowl-in piston design comes into play, right? So if I now draw in the piston design, usually this is when you see these bowl-in piston type of designs, right? Where this bowl that's kind of machined into the piston is basically meant to contain the fuel spray, right? It's meant to actually act as almost like a deflector shield where the fuel comes in and kind of deflects off of that bowl, and then it helps spread the fuel to, again, different parts of the cylinder. And of course, turbulence plays a key role, and as you already know, we can design in different levels of turbulence based on the combustion chamber design. Now, the chemical mechanism is, in fact, what combustion scientists would call ignition delay, right? So this chemical mechanism part that I'm referring to is what, the scientists would refer to as ignition delay. And so this, of course, is that once that fuel is ignitable and it reaches the ignition temperature, there's still a time period, right? There's still a period of time where, your bonds basically have to start separating, and you start generating the radicals that eventually lead to runaway ignition, right? Spontaneous ignition. And so that depends more on the composition of the fuel, right? The fuel type and the air. We talked about this a little bit in the spark ignition combustion chapter. And of course, your in-cylinder conditions also play a role at accelerating or decelerating that ignition delay. Okay, so now the ignition delay, of course, is sort of explicitly or inversely related, if you will, to the amount of premixed combustion. And the amount of premixed combustion, therefore, controls the amount of diffusion combustion. You only have a certain amount of fuel that you can inject into the cylinder. And so if you're burning more of your fuel in a premixed fashion, that means that you're going to burn less of your fuel in a diffusion fashion. And all of these are controlled by the timing at which the fuel gets injected into the cylinder, right? So if I go back a few slides, remember this slide here where we said that start of injection is here. Well, just like spark advance, we can advance or retard that start of injection, right? So advancing would be if we were to move start of injection, further away from top dead center. And retarding is if we were moving start of injection closer to top dead center or later in the cycle is a better way to say it, because of course top dead center becomes a relative way of quantifying advance and retarding. Okay, so advancing start of injection means, moving injection earlier in the cycle. Retarding start of injection means moving injection later in the cycle. Okay, so by doing that, by changing your injection timing, you change your ignition delay. Okay, and by changing your ignition delay, you change the amount of time you can premix your fuel. And so if you lengthen your ignition delay, you increase the time that you can premix your fuel. So you increase your premix burning, which means you decrease your diffusion burning. Okay. And by the way, the other thing that we really haven't talked about here is the combustion duration. And the combustion duration is just that. It's the time from start of combustion to end of combustion. Right? So let me just kind of quantify or define these things. We already know what ignition delay is, right? That's the time between start of injection and start of combustion. And then we have combustion duration. And this is the time between start of combustion and end of combustion. So if I increase the extent of my premixed burning, well, you can already tell that premixed burning burns relatively faster than diffusion burning, right? Look at the amount of time this takes compared to the amount of time this takes, okay? And so if I increase my premix burning, I decrease my diffusion burning. Premix burning occurs faster than diffusion burning. And so if I increase my premix burning, I decrease my combustion duration. If I shorten my ignition delay, decrease my amount of premix burning, increase my diffusion burning, I will therefore increase my combustion duration. Okay? Okay, so, and how does injection timing play into this? Well, generally speaking, if we advance injection timing, when the injection timing is still before top dead center, then what we're doing is we're introducing the fuel into a relatively colder environment where the physical processes, right? Remember, think about this physically. The physical processes are penetration, breakup, atomization, and vaporization, right? You know physically, based on your own experiences, that if you heat something up, it's going to be a lot easier to atomize it and vaporize it. So if you cool it down, it's going to be harder. It's going to take more time to do those processes, right? So when you introduce a fuel into a colder environment, you basically increase the amount of time that it takes to physically prepare the mixture for burning, okay? So that will increase your ignition delay. And so as you increase the ignition delay, you increase the fraction of premix burning and you decrease the fraction of diffusion burning, okay? And you can actually see that in this plot here that's shown on this slide. So this is what we call the heat release rate, but you can think of that as basically the same idea as the fuel burning rate of the mass, okay? The fuel mass burning rate. And we have 4 different injection timings that we're looking at. 7 degrees before top dead center, 13 degrees before top dead center, 19, and 25, right? So as we go down the list, we're advancing injection timing, okay? And so this plot that you see here, right, this is the 7-degree injection timing, and this real spiky dashed curve that you see here, that is 25 degrees before top dead center injection timing, right? And look at the difference in premix burning, right? This is the premix burning for the 7 degrees. This is the premix burning for the 25 degrees, okay? All because that advance in injection timing increased the ignition delay, which increased the amount of time to prepare the fuel for burning. And so once ignition conditions were reached, there was a lot more fuel that was premixed and ready to burn, so it lit off and created a huge premix spike, and consequently, look at the diffusion burn, right? Consequently, a much lower diffusion burn as opposed to the 7 degrees, which, look at its diffusion burn. It's much higher and much longer, of course, okay? Okay, so because, as I mentioned, this premix combustion has a faster burn rate than diffusion combustion, there tends to be this inverse relationship between ignition delay and combustion duration, right? And again, combustion duration is that time between start of combustion and end of combustion. And so, and by the way, this plot here is from my PhD dissertation, which is, getting kind of old now. I don't want to talk about it. But anyway, the point is that, so we're plotting ignition delay. So this curve here, this dark curve here is the ignition delay, okay? And then that's as a function of the fuel injection timing, degrees before top dead center. And then we have over here this dash dot or long dash, short dash curve is our combustion duration, okay? And what you'll notice is that as we advance the injection timing, right, our ignition delay increases, but our combustion duration decreases, right? There's that inverse relationship. Now, of course, what I was studying for my PhD was actually a novel type of combustion, something which we still study to this day, called premix combustion. And so the whole idea is to create, remember how we said early on that we want to try and create as much premix combustion as we possibly can to avoid generating soot, right? And so, we're not going to get into it in today's lecture, but when we do that by advancing injection timing, what ends up happening is we end up introducing the soot-NOx trade-off, okay? where basically as we advance timing, we increase the amount of premix burning, which decreases soot, but that also substantially raises temperatures, right? That higher release of energy with premix combustion results in higher temperatures in the cylinder, and so that tends to increase NOx, right? More premix burning, decrease soot, but you increase NOx, okay? The soot-NOx trade-off. So that's not good. So we then say, okay, well, what happens if we create a premixed burn by retarding injection timing? And so that was one of the things that I looked at in my PhD. And of course, what you see by retarding the timing from this 10 degrees before top dead center, eventually what happens is we kind of overcome the hump of the piston motion, and the cylinder temperatures begin to drop again. And so the ignition delay begins to raise, right, which causes the combustion duration to decrease. And then if we retard our timing even more, then the ignition delay really increases and the combustion duration substantially drops, right? So we end up getting this to be all premixed burning at this very late timing because of the very long ignition delay. And then what this allows us to do is to simultaneously reduce soot and NOx, okay, as opposed to the conventional trade-off that we experienced under traditional engine designs. So anyway, it's fun work. We still work on it today. It's one of the things that I enjoy doing. Okay, so we also recognize that the extent of premix combustion versus diffusion combustion depends on the load condition of the engine, right? So when you're at a low load operating condition, you have basically almost all premix burning, right? Now you see here in this burn profile, my eyes are right here. In this burn profile, you'll see that there's actually two modes of burning, right? What these are is they're actually two humps of premix burning, okay? And the reason why that's happening is because we're using something which we call pilot injection, okay? So pilot injection is a type of technology that was introduced in diesel engines in the last several decades as basically, again, a means to try and create as much premix combustion as you possibly can. And as you can see, even though we're at a low load condition, it works quite well, right? You have basically two modes of premix combustion. Now, when you go to a high load condition, and now we're completely in a single injection fashion, right? You'll notice that this is the rate of fuel injection. Okay, so this is rate of fuel injection. I should have told you that over here, right? This is the rate of fuel injection as well. Now, if you look at this curve, right, what you'll notice is that it looks real similar to this one right here, right? You see the similarities where you basically have a rise in the fuel that's injected, it kind of stabilizes, and then it drops as you end injection, okay? And that's exactly what's going on here. You have a rise in the rate of fuel injection, stabilizes, and then it eventually drops, okay? Now, because this is a high load condition, right, our combustion, this is SOC, this is where we begin combustion, and you'll notice that, we've not even delivered probably 90% of the fuel that we're going to deliver over this combustion event, right? And again, it's a high load condition. We're trying to make torque, so we're going to have to introduce as much fuel as we possibly can into the cylinder, right? And so as a result of that, you have a small amount of premix combustion and then mostly diffusion combustion during the burning period, okay? Okay, so that is basically as far as I'm going to be able to get you. It's as far as we would have gotten if we had covered this in class. Of course, if we had had that last week of class, you actually would have had this be part of one of your lab exercises. As you might recall, we modified Lab 4 for y'all so that it was more attainable given the shortened and the craziness of the COVID semester. But this is basically all the lecture material that I would have provided you during the semester. And I just want to leave you here with this somewhat lyrical presentation that was given by a fellow named Sir Harry Ricardo. Okay, some of you may have heard of Ricardo. They're actually a fairly popular engine research organization in England, as you might guess. The founder, Sir Harry Ricardo, was from Great Britain. Okay, and what he's really known for, though, is he's really known for pioneering the design and development of specifically the high-speed diesel engine. So again, if you watch that YouTube video on the technology of diesel engines, what you'll learn is that Rudolf Diesel never, ever, ever intended his engines to be used in an automobile. Absolutely not. He, look at the size of the engines that he was making at that time. What he was really trying to do was he was trying to supplant the steam cycle, right? So he wanted to have megawatt diesel engines as opposed to megawatt steam turbines in electrical generating power plants. That's what he was after, right? So his engines were all just massively huge. But Sir Harry Ricardo recognized that the concept of the diesel engine could be miniaturized, if you will, to the size of an automotive engine. And so he spent considerable amounts of time basically pioneering the high-speed diesel engine, or the high-speed compression ignition combustion engine. Now, what is provided to you here in this text is actually taken from a lecture that he gave to the Royal Society of London. Okay, can you imagine today, if you get a chance, go and take a look at the kind of lectures that the Royal Society of London hosts today, and ask yourself, would they ever let someone in to talk about engine technology today, right? I would love to think that they would, but there's a part of me that just kind of doubts that they ever would. But he gave this talk to the Royal Society of London, I think in 1923, and you'll have to don't quote me on that. I actually have the original lectures, the whole full suite of lectures. If you're ever interested in seeing them, he goes through and basically over a period of 3 lectures. It wasn't just one. They actually invited him back 2 more times. Goes through and talks about the thermodynamics of engines and power generation and how you control them and all kinds of just really cool state-of-the-art stuff for the 1920s, right? And basically, he kind of concludes by saying the following, and I'm going to read this to you. And as I read it to you, first of all, if you want to imagine yourself sitting in a coffee shop, for poetry hour, sipping on your latte, having someone read this poetry to you, you're more than welcome to. But what I also want you to think about is the fact that it was 1923 when he wrote this, right? And think about the insight that he had without having laser diagnostics and high-speed in-cylinder photography or videography or even things like electronic pressure transducers and data acquisition systems. I mean, you had engineers standing around taking data by hand, pen and paper, right? Just basically using their intuition as to what was going on inside the cylinder of an engine, right? I find that remarkable, and I find that kind of a true testament to the spirit of innovation that you, even to this day, find in engineering, but of course in different applications, right? In broad sets of applications. So as I read this to you, what I'd really like to do is to challenge you to think about the way that you approach engineering, right? And the type of physical sense that you have with engineering. Don't think of it as just equations and fundamental science and project management and getting things done. I mean, those are all elements of engineering, of course, right? I'm not saying that it's not, but also think about your own physical intuition of what is going on with that which you are engineering, right? What exactly is that drill bit doing, or what is that drag reducent agent in the fluid actually doing, right? Think about things physically, and I think that you'll have a far better appreciation for the work that you do as an engineer and the impact that you can have on society through improving technology. Okay, here we go. Before concluding, I'm going to take the rather unconventional course in a technical lecture of asking you to accompany me in imagination inside the cylinder of a diesel engine. Let us imagine ourselves seated comfortably on the top of the piston inside the cylinder, that was a Jacobs insertion, at or about the end of the compression stroke. We are in complete darkness. The atmosphere is a trifle oppressive, for the shade temperature is well over 500 degrees C, that's even hot for Texas standards, almost a full red heat. And the density of the air is such that the contents of an average sitting room would weigh about a ton. Imagine having a ton of pressure on you, right? You literally are holding a ton of weight on you. Also, though, it is very drafty. In fact, the draft is such that, in reality, we should be blown off our perch and hurled like autumn leaves in a gale. Suddenly, above our heads, a valve is opened, and a rainstorm of fuel begins to descend. I have called it a rainstorm, but really the velocity of the droplets approach that of nearly rifle bullets rather than raindrops. For a while, nothing startling happens. The rain continues to fall. The darkness remains intense. Then suddenly, away to our right perhaps, a brilliant gleam of light appears, moving swiftly and purposefully. In an instant, this is followed by a myriad others all around us, some large and some small, until on all sides of us the space is filled with a merry blaze of moving lights. From time to time, the smaller lights wink and go out, while the larger ones develop fiery tails like comets. Occasionally, these strike the walls. But being surrounded with an envelope of burning vapor, they merely bounce off like drops of water split on a red-hot plate. Right overhead, all is darkness still. The rainstorm continues, and the heat is becoming intense. So what did we just describe there? We described start of injection, ignition delay, and premixed combustion. So let's keep reading. And now we shall notice that a change is taking place. Many of the smaller lights around us have gone out, but new ones are beginning to appear more overhead and to form themselves into definite streams shooting rapidly downward or outward from the direction of the injector nozzles. Looking around, again, we see that the lights around are growing yellower. They no longer move in definite directions, but appear to be drifting listlessly hither and thither, here and there. They are crowding together in dense nebulae, and these are burning now with a sickly, smoky flame, half suffocated for want of oxygen. Now we are attracted by a dazzle overhead, and looking up we see that what at first was cold rain falling through utter darkness has given place to a cascade of fire as from a rocket. For a little while this continues, then ceases abruptly as the valve closes. So what did we just describe there? We described diffusion burning, the mixing controlled combustion. He describes it as a cascade of fire. I described it as flamethrowers coming from the nozzle of the fuel injector. Above and all around us are some still lingering fireballs, now trailing long tails of sparks and smoke and wandering aimlessly in search of the last dregs of oxygen, which will consume them finally and set their souls at rest. And so, of course, that last bit there is the end of combustion, that particle droplet burning as we now describe. If so, well and good. If not, some unromantic engineer outside will merely grumble that the exhaust is dirty and will set the fuel valve to close a trifle earlier. So ends the scene, or rather my conception of the scene, and I will ask you to realize that what has taken me nearly 5 minutes to describe may all be enacted in 1/500th of a second, or even less. With that, ladies and gentlemen, I thank you so very much for participating in this extended Spring 2020 semester lecture. I hope you all are having a great semester. Remember to stay in touch, and we'll talk to you all later. Take care. Bye-bye.